So now let's start examining the real nitty-gritty here. And that's the fact that the world isn't perfectly flat. We have hills, we have inclines, and that's going to change our friction. And I can point this out to you very easily. If I hold this brick on this ramp, I want you to consider the free body diagram here. And what's happening? The brick has a weight that goes straight down. The board or the ramp provides a normal force against the weight, kind of. Remember, the normal force acts perpendicular to the contact. So when the brick was like this, my normal force worked directly against the weight. When my ramp is like this, my weight still is pointing straight down, but my normal force is actually like this because it's perpendicular to the ramp. So that's a case where now my normal force is not as big as it once was. Here, my normal force is equal to all of the weight of the brick. Here, the normal force is actually less because the weight is still pushing straight down or pulling straight down, but my normal force is now at an angle. What else is acting on this brick? Is there a force that is pulling this brick down the ramp? You should realize there is. That gravity wants to pull things down the hill, but the brick's not moving down the hill. We know there's a force pulling that way. What's keeping the brick on the ramp? That's friction. So there's a component of the brick's weight caused by gravity that is pulling this way, and there is friction that keeps it from sliding down the ramp. Now, same situation here. Now there's a lot more pull from gravity down this ramp, but it's still not a big enough pull to overcome the friction. We still have weight pulling straight down, but now my normal force is even less because my angle is steeper. If I eventually get to a point, you know what's going to happen. If this ramp gets steep enough, the motion of the brick changes. Once the ramp got steep enough, the pull of gravity down the ramp was enough to overcome the friction that was keeping the brick stationary. And you saw what happened. The motion of the brick changed. It slid down the ramp. Well, remember that the frictional force is determined by two things. That coefficient of friction, which is whatever two surfaces are in contact. I didn't change. It was brick and wood the whole time. My normal force was getting less as I raised the ramp. So as this got less, that means the frictional force got less. And eventually the frictional force was so little that gravity was able to overcome it and the brick started to move. Now, we need to draw a free body diagram of this to be able to describe the forces that are in play here. Okay, so on a flat surface, here's what we've got. Got a brick in contact with the surface. Nobody's pushing or pulling on it, not introducing friction here. We've got the weight pulling down and the normal force pushing up. Now let's look at what's different here. Here's my brick on an inclined plane. I still have a weight of the brick pulling down. That doesn't change. It still has a mass, and it's still being pulled towards the center of gravity down here towards the earth. The weight always acts directly down. But remember that the normal force is perpendicular to contact. So because the ramp now, the surface is now at an angle, the normal force is also now at an angle. Imagine this. If I brought this angle down, 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 down until it got flat, the normal force eventually ends up being perpendicular, being the same as the weight. If this angle gets bigger and bigger and bigger, this vector here, this normal force ends up being less and less and less. Think about a vertical board. It doesn't push against the brick at all, and the brick would end up falling straight down. So we have this angle here measured. Let's call it theta. And for now, it's just going to be a generic angle. We can put in a number, and we will when we get to that point. Now, I can go through the geometry of this, and I know how much you guys love geometry. And if you want me to prove this to you, I would be more than happy to go through this. But you can kind of see that there's some right triangle stuff in here going on, that we can take this angle and, with parallel lines and all kinds of, we can make some triangles, and then we can do that Sokotoa stuff, and we can figure out of this weight, what portion of it is going down the ramp and what portion of it is pushing away from the ramp equal to the normal force. And I'm just going to go ahead and give this to you, and you're going to copy this down. The force that gravity pulls down the ramp. Now, mg, we've seen mg, that's equal to the weight. It's mg sine of theta. It's the weight of the object, but it's only part of the weight of the object, because it's kind of like when we did two-dimensional motion and we had something with a velocity at that. We know some of it was in x and some of it was in y. Well, now when we have an angle, some of the weight is working one direction and some of the weight is working the opposite direction. And what happens, the force of the weight coming down the ramp is found by mg sine of theta, and the normal force, as you can probably guess, is mg cosine of theta. Now, we also have a force of friction. And the force of friction is that. It is whatever the two surfaces are times the normal force. And the normal force is some function of the object's weight. If this ramp were totally vertical, there wouldn't be a normal force and it would go straight down. There wouldn't be any friction because they wouldn't be in contact anymore. And the force pulling something down would be just equal to the weight. It'd be like there wasn't a ramp there. So this is a very important relationship. Like I said, I could go through the geometry of this, but what you need to recognize is have this and realize, okay, the force that pulls something down a ramp is its weight, mg is the weight, times the sine of whatever that angle is. The normal force now is mg cosine of theta, the weight times the cosine of whatever that angle is. Weight is still weight, it still works down. And that the frictional force is this right here. Now, as this angle gets bigger and the friction and the normal force gets smaller, means the friction gets smaller. And this is why a really steep ramp, things slide down easy, because the friction ends up being really small. If this angle gets pretty short, pretty tiny, well, the normal force gets bigger, which makes the friction bigger. Things don't slide down a gradual ramp on their own very easily because the friction is just too big. Okay, so now I think you've got this diagram